Hello, my name is Eduardo Barrocio, and I'm Director of the Composites Additive Manufacturing and Simulation Consortium at Purdue University. Today, I would like to walk you through how do we use simulation to drive part and tool shape design for large-scale additive manufacturing. So I would like to use this example of a autoclave part. So we started with the predicting and compensating for the shape change that the part exhibits as it's being processed in an autoclave operation and then cooled down to the ambient temperature. Then that drove the design of a LSAM additive tool, but the additive tool also exhibits an isotropic shape change, which we predict and compensate for. And then we combine the part and the tool to capture the interactions of the two and ensure that we produce the right part shape. So all this exercise was carried out with the virtual twin of the manufacturing process called ADDITIVE3D. ADDITIVE3D was developed with the goal of enabling first-time right printing, and it starts by the G-code that is produced after the slicing process. We use that G-code to drive a virtual twin of a manufacturing process where we can predict the evolution of temperature, polymer crystallization, if we're printing with a semicrystalline polymer, residual stresses, deformation. But we don't stop there. We can also predict the performance of the as manufactured shape. In other words, how the part is going to creep as it's subjected to multiple autoclave cycles if it's an autoclave tool, or how the shape of the printed tool is going to occur as it's being heated or cooled down in an autoclave operation. So this way, we can ensure that we can produce the right part shape the first time. So let me now dive a little bit into what is under the hood of ADDITIVE3D. So ADDITIVE3D requires two inputs. One is the machine card and the other one is the material card. So the machine card includes information such as the effect of flow in the orientation of fibers, the interaction of the printed material with the substrate, as well as the ambient conditions inside the printer. The material card includes information about or information parameters required for the different material models that are used to describe different set of physics that occur as the material is printed and cools down to the ambient temperature. So both the machine and the material card inform the process simulation, where we carry out a sequentially coupled thermomechanical analysis to allow us or to provide predictions of temperature, residual stresses, deformation, and allow us to iterate virtually and mitigate problems such as delamination, excessive deformation that might occur during the print process. And then we can connect all the way from the manufacturing to the performance of the as manufactured shape. In other words, if we are printing tooling or molds, we can predict the shape change of that tool when it's in the operating conditions, considering all the steps and considerations in the manufacturing process. Now, there's been multiple years of development around ADDITIVE3D and integrating this technology, multiple PhDs, and we have streamlined this technology to put it at the fingerprints of the users through an industrial consortium called CAMS, or Composite Additive Manufacturing and Simulation Consortium. So this application, as you can see, is really easy to simply drag and drop the machine code, select the printer that you're going to use, select the material, process conditions, and within a few clicks, basically set up a simulation that can run on a high performance computing system or HPC. And then once the simulation has completed, you can have a visualization of the simulation results in the same application, as you can see in this case for the predictions of the formation of this part. I would like to dive a little into the physics that are captured in ADDITIVE3D. So the process starts with the flow of a suspension of fibers in molten polymer. As that suspension flows through a nozzle, turns 90 degrees and is compacted, there are different flow mechanisms that develop and that affect how fibers are oriented within the printed material. So we have a predictive simulation technology to capture the effects of flow in the position and how that affects the fiber orientation. I'm going to talk a little bit more about that in just a minute. But then once the material is deposited, there is a compactor that provides consolidation and allows mitigating gaps in between adjacent beads. But the compactor is also actively cooled down to prevent the material from sticking to the surface. So in Additive 3D, we capture heat losses due to that compactor as it moves around the print. Then we also capture heat losses due to convection, radiation, conduction. We capture fusion bonding, uh, which involves polymer diffusion, temperature, crystallization in the case of semicrystalline polymers. And we capture the solidification phenomena that on the one hand involves shrinkage due to not only the coefficient of thermal expansion, but also due to the polymerization, to the polymer crystallization. And on the second hand, we also capture the stress relaxation that the polymer exhibits at elevated temperature through an isotropic thermoviscoelastic material formulation. And then the last but not least important, we have different modeling techniques to capture different types of build plates or substrates uh, in both on both the thermal as well as the mechanical interactions of the printed material with the substrate. Now, just to briefly mention a little bit about the flow, the flow simulation. So we start with a viscous anisotropic constitutive relation, where basically we have an anisotropic viscosity tensor that depends on microstructural characteristics such as the orientation tensor, the fiber volume fraction, and the fiber length. And then we also use Jeffreys equations for fiber orientation evolution. This framework is implemented in a SPH numerical technique where we represent a cluster of fibers by a sphere and which has a orientation vector that is tracked explicitly throughout the analysis. Just to show you an example of the flow simulation prediction, so you can see here orientation that develops as the material is being deposited, how that orientation evolves as it's being compacted. In this case, the lighter the color is, the higher the fiber alignment in the print direction. And then we can also investigate, for example, how does the deposition of adjacent beads interacts with the previous bead and affects also the fiber orientation and the effect of compaction, right? The effect of compaction on closing the gap in between the beads, as well as reorienting fibers that are slightly misaligned in the from the print direction. Then we incorporate the set of physics that I just walked you through, and we represent the process of depositing material bead by activating elements in a finite element mesh. At the same time, we capture the local orientation of the material within the entire print. So you can see here on the upper right hand side a comparison of the physical print versus the finite element mesh that is automatically generated with Additive 3D. Now we have developed a key partnership with Thermwood that has led to the establishment of the Thermwood LSAM Research Laboratory with the goal of enhancing the confidence and supporting the large-scale additive manufacturing industry. The LSAM laboratory features an LSAM 10.5, which has a build envelope of 10 by 5 by 5 feet, is equipped with a 40 millimeter melt core, and can print at rates of nearly 250 pounds an hour. Here in the middle, you can see the LSAT system. It's a 5-axis router that allows to do the finishing on parts that can on parts of that scale that can be printed in the LSAM. And then on the right-hand side, you can see the Cambry system, which stands for Composites Additive Manufacturing Research Instrument, which was developed at Purdue and used extensively for material development, validation, characterization, etc. So I would like now to focus on the tool demonstration that we are featuring in this presentation, and it's a tool to produce this double curve shape that represents the geometry of an air inlet duct. So you can see here on the right hand side the tool design for the large scale additive manufacturing process. So one of the motivations for choosing this geometry is the amount of a spring back that both the part and the tool develop as they are produced in the autoclave operation. So just to walk you again through the workflow to drive the part and tool shape compensation. So we started with the part definition or the part geometry definition. Then we predicted the shape change due to the anisotropic shrinkage of the material and compensated for this shape change. And then using the compensated shape change, we developed a tool design for the additive process. But again, the printed material is also anisotropic. So we predicted then the shape change of a printed tool as the temperature is raised from the ambient to the autoclave temperature. And then we carry out an analysis where we integrated both the part and the tool, as well as its corresponding interactions to ensure that we produce the part, the right composite part geometry. And then we iterate virtually using this workflow to attain a part geometry that is as close as possible to the nominal part shape that we started with. So just to illustrate the additive process simulation, so the inputs that we need are the machine code, the material card, the machine card, and then we can predict, for example, residual stresses, deformation. So in here, we can look at from left to right to the evolution of temperature throughout the print process. So you can notice the large temperature gradients that develop from the bottom to the top, as well as across the thickness of the printed part. At the middle, we're looking at the stresses in the layer stacking direction or in the Z direction. And as you can see, stresses are primarily localized in the corners, where actually is more prone to for the lamination to start. And then on the right-hand side, we can look at the deformation in the Y direction. So as you can see here, as the part is being printed and then released from the substrate, it actually springs in as well. So the tool has been compensated for that spring in. So in other words, we printed a tool that is slightly open to accommodate this spring in deformation so that at the end, we can have material for the machining operation. We also investigated the shape stability of the printed tool after multiple autoclave cycles. So you can see here the layup that was made on the printed tool after the tool was in the autoclave, in an autoclave cycle at 350 F or 180 Celsius and 80 psi. Then after the autoclave cycle, both the part and the tool were laser scanned. And then we basically investigated the shape stability of the tool after multiple cycles, specifically after 10 cycles. So as you can see, the shape change of the tool is within 150 microns from the nominal shape. And the parts generally are within 200 microns, 200 to 250 microns from the design shape. Approach to enable first-time right printing driven by a virtual twin for additive manufacturing called ADDITIVE3D. I would like to share how you can access this simulation uh, technology through the CAMS Consortium. So the CAMS Consortium was established with the goal of enhancing the confidence in the large-scale additive manufacturing technology by providing access to simulation tools that have been developed on a strong scientific foundation. So through the CAMS Consortium, members can access Additive3D for first-time right printing. We have both a standalone and a web-based application. We also offer access to the LSAM system or CAMBRI for printing studies, demonstrations, material development, material characterization. We provide quarterly webinars focused on addressing problems that have been posed by members of the consortium and providing practical solutions grounded on scientific understanding of the process. And last but not least important is we also provide technical support to close any gaps that could be left in the other points that could be focused, on additive 3D, printed trials, workflows, material characterization, development of material cards, etc. I would like to finalize by just providing my contact information in case you have any questions related to CAMS or related to the activities in the ELSAM Research Laboratory. Thank you and have a great day.